Good morning, everybody. Today we will discuss very important points from physics that underlie the application of some physical phenomena in medicine. Today, our guest will follow ionizing radiation, its types, physical foundations, and of course, applications. And we must also understand the important thing how harmful ionizing radiation is and how we can use it in medicine without harm or with minimal harm to the human body. Let's start our conversation by defining what radiation is. Radiation is the transfer of energy in the form of waves or particles through space or through a material environment. Radiation is often classified as ionizing or non-ionizing, depending on the energy of the emitted particles. And we will smoothly move on to the important point today. This is ionizing radiation. Ionizing radiation is radiation, the interaction of which with the medium leads to the formation of ions of different signs, that is, to the ionization of the medium. Ionization of the medium. Such properties are possessed by radioactive radiation, high energy radiation, X-rays, and etc. Visible light and ultraviolet radiation are not classified as ionizing radiation. Ionizing radiation carries more than 10 electron volt, which is enough to ionize atoms and molecules as well as break chemical bonds. This is an important distinction due to the large difference, the terminal effects to living organisms. What in the surrounding life can be a source of ionizing radiation? A common source of ionizing radiation is radioactive materials that emit alpha, beta, or gamma radiation and consisting of helium nuclei, electrons or positrons, and photons, respectively. Other sources include X-rays from medical research radiography, as well as mesons, positrons, neutrons, and other particles that make up secondary cosmic rays that are formed after the primary cosmic rays interact with the Earth's atmosphere. That is, in fact, around you and me, there is ionizing radiation in which you and I are used to living. Gamma rays, X-rays, and the higher energy range of ultraviolet light make up the ionizing portion of the electromagnetic spectrum. The word ionize refers to the detachment of one or more electrons from an atom, a process that requires relatively high energy provided by electromagnetic waves. Further, along the spectrum are non-ionizing energy sources from the lower ultraviolet spectrum, which can't ionize atoms, but can break the interatomic bonds that form molecules, thereby destroying them, and not atoms. An example of this sunburn caused by the sun's long wavelength ultraviolet light. Waves with a wavelength longer than ultraviolet is invisible. Infrared and microwave frequency range can't break bonds. We regard their effect as thermal due to vibration in interatomic bonds. Radio waves and below, as a rule, are not considered harmful to biological system. They are classified as non-ionizing types of radiation. And on the picture you can see the example, the scale of ionizing or not ionizing, the scale of electromagnetic waves, where lays ionizing radiation and non-ionizing radiation too. So, we will begin our conversation about Ionizing radiation with X-rays. What is about X-rays? Firstly, historic information that X-rays were first discovered by Röntgen in 1895. This is electromagnetic radiation that occupies the spectral region between gamma and ultraviolet radiation in the wavelength range of the 10 to the power minus 12, the 10 to the power 7 meters. You can see X-rays. So the boundaries of this range are somewhat arbitrary since long-wave X-rays overlap with short-wave ultraviolet radiation and short wavelength with long-wave gamma radiation. It's generally accepted that the conditional boundary between X-ray and ultraviolet radiation is wavelength 18 nanometers. X-rays of short wavelength are called hard, and long wavelengths are called soft. To measure the wavelength of X-ray radiation, an off-system unit of length is sometimes used angstrom. 1 angstrom is the 10 to the power minus 10 meters or the 10 to the power minus 8 centimeters or 0.1 nanometers. As for the energy, we are also interested to know what energy will the X-ray quanta have at the radiation boundary. The energy of X-ray quantum at the boundary wavelength 18 nanometers is determined by the Planck's formula, that E is h constant Planck multiply on frequency, yeah. And what is this? We can use that frequency is frequency is velocity divided by the wavelength. And so what is about h? H is the Planck's constant, and its number is 6.62 multiplied on the 10 to the power minus 34 joules. So nu or f, small f, is the frequency of the electromagnetic wave. We remember that the frequency of an electromagnetic wave through the speed of light in a vacuum and the length of this wave is equal to the ratio that speed of electromagnetic wave or speed of light is 3 multiplied on 10 to the power 8 meter per second in vacuum. Yeah, let's substitute in the known formula and get the value of the quantum energy, and the quantum energy will be 25 multiplied on 10 to the power minus 19 joules. And so X-ray radiation is electromagnetic radiation with a wavelength less than 80 nanometers, and the energy quanta is more than 25 multiplied on 10 to the power minus 19 joules. Let's now consider the option: how can you and I get X-rays in our life? Maybe in medicine too. We can receive X-rays with the help of X-ray tube. What is about X-ray tube? This is an electric vacuum device for generating X-ray radiation, in which generation occurs due to bremsstrahlung of electrons accelerated to an energy of more than 10 kilo-electron volt. So, how does an X-ray tube work? Let's see on the picture, and we must say the main parts of the tube. And the main parts of the tube are anode, cathode, and we must also remember that there is a vacuum inside the tube. And there is a window, yeah, inside the glass vacuum, yeah, through the X-ray radiation or X-ray beam can go. What happens in the X-ray tube? Let's see on this animation. Firstly, the filament of the cathode, thanks to the current from a special low voltage source, has a surface temperature of the order of 2000 to 2500 Kelvin, at which electrons are pulled out of the filament. This is called the phenomenon of thermoionic emission. These electrons are immediately picked up by the strongest electric field. The voltage between the cathode and the anode, created by a special high voltage source, can be regulated in the range from several kilovolts to hundreds of kilovolts. The focusing electrode is an electrical contact with the filament so that it can be considered part of the cathode. Its task is to bend the lines of force of the accelerating field so that the electrons form a narrow beam despite their mutual Coulomb repulsion. So, the anode of X-ray tube is made of heavy refractory metals, maybe molybdenum, and the deceleration of electrons is accompanied by the appearance of X-ray radiation. But the current in X-ray tube is very small. It's determined by the very modest performance of the filament, the number of electrons escaping from it in 1 second. So, the current in X-ray tubes is not measured in amperes, but in milliamperes. But the anode voltage is enormous, so that the electric power of the tube turns out to be quite tangible, about 0.5 kilovolt. That is, it turns out that the total power of the flow of fast electrons on the approach to the anticathode is 500 volt. So, the total power of the X-ray flux arising from the deceleration of electrons is about only 1% of this value, that is 5 volt, and the remaining 99%, and that is 495 volt, is the heat released and the anticathode or anode. It turns out that 99% of energy that we receive in the tube is heat, really. Therefore, the main element of the tube is also the cooling system, which prevents it from overheating during operation. And let's see on the animation what happened. We have an electric energy and give this electric energy to the tube. What happened in the anode? Maybe will be the phenomenon of thermoionic emission, and electrons go to the anode, and after that we will have the X-ray beam again. Electrons go from cathode to anode, and after that we will have the X-ray beams. And don't forget the tube efficiency is only 1%. 99% heat generated at the anode, or anode we can say anticathode. We can say the same name. So earlier we have already discussed that according to the laws of electrodynamics, and when any moving electric charge is decelerated, electromagnetic radiation arises. Moreover, the frequency of this radiation is greater, the greater the negative acceleration of the moving charge. If a charged particle has a large kinetic energy and experiences a sharp deceleration, then X-ray electromagnetic radiation appears. Bremsstrahlung is radiation that occurs as a result of deceleration of electron by the electrostatic field of the atomic nucleus and atomic electrons of the anode substance. Bremsstrahlung X-ray radiation occurs when the voltage across the tube is about 10 to the power 4 volt. So, at lower voltages, the predominant processes in the collision of an electron with atoms are the processes of thermal excitation and ionization, and there is no X-ray radiation. So, Bremsstrahlung X-rays are emitted by electrons when they are decelerated in an electric field. Its properties don't depend on the substance of the X-ray tube anode. According to the laws of classical electrodynamics, Bremsstrahlung, like visible white light, must have a continuous spectrum. Therefore, it's sometimes called white radiation, and all wavelengths from 0 to infinity must be present in spectrum of this radiation. And what Bremsstrahlung properties may be that X-rays are emitted by individual photons. All electrons reaching the anode have the same kinetic energy equal to the work of the electric field between anode and cathode. The kinetic energy of an electron is partly transferred to the substance and goes to heating it. Q, heating, and partly is spent on creating an X-ray quantum. And the last, the relationship between the amount of heat and the energy of electron is random. So let us consider the origin of X-ray quantitatively. In fact, we know that all electrons reaching the anode have the same kinetic energy, equal to the work of the electric field between the anode and cathode. Let's see the first formula. How can we calculate the energy? So, when electrons are decelerated in the anode material, this kinetic energy is converted into the energy of radiation quantum and heat. This energy converted into heat and electric quantum. So, for one electron, it's impossible to predict where its energy will go, into radiation or into heat, because this is a random process, how I said earlier. So, in the flow of electrons accelerated by the voltage U, some of the energy released during deceleration at the anode is converted into the energy of X-ray Bremsstrahlung quantum. Since the relationship between the terms of energy and heat is random, the emerging radiation exhibits very different frequencies. The spectrum of Bremsstrahlung X-ray radiation is continuous. In this spectrum, for each voltage value U, voltage, there is a short wavelength boundary that determines the maximum possible frequency of X-ray quanta minimum wavelength. Let us express from the corresponding ratios, assume that Q, so heat energy, is zero. All the energy of the electrons is converted into radiation, and knowing that magnitude of the voltage U, we calculated the numerical value of minimum wavelength in the spectrum of X-ray radiation. We have what we have, the last formula. So we have that what we can put in spite of energy, this energy, we can put our energy, so how I said earlier, and through this formula we can calculate the wavelength, minimum wavelength of radiation, and calculate it through the electron volts, and this last formula characterizes the minimum wavelength of X-ray radiation in angstroms. So the experimentally obtained X-ray Bremsstrahlung spectra at various voltages across the X-ray tube are shown in the figure on the slide. The ordinate is the value of spectral density of X-ray radiation flux. That is, the ratio of the energy emitted in a narrow wavelength interval from a unit area per unit time to the width of this interval. Wavelength. So, in the direction of long waves, the intensity curves in the figure fall off gently, asymptotically approaching zero with increasing wavelength. On the shortwave side, the intensity curves cut off abruptly. The wavelength lambda minimum wavelength corresponding to the short wavelength boundary of continuous X-ray radiation. It's known from experiments that the minimum wavelength is inversely proportional to the voltage on the X-ray tube, which fully correspond to our formulas, which we talked about earlier. According to these formulas, as the voltage between the anode and cathode of the X-ray tube increases, the minimum wavelength is the X-ray Bremsstrahlung spectrum decreases. So we can see. And therefore, the radiation becomes harder. Thanks to this, it's possible to regulate the hardness of radiation in X-ray machine, the so-called kilovolt parameters in practice medicine. So, beginning with certain voltage values on the X-ray tube, sharp lines appear against the background of the continuous X-ray spectrum. Yeah, this is continuous spectrum and maybe what? Maybe sharp lines appears. Yeah, so the appearance of this linear spectrum can't be explained by inhibitory effects. Such radiation is called characteristic and consists of their regularly spaced razor narrow spectral lines. Their wavelength depend solely on the material of the X-ray tube anode. The characteristic radiation arises when an electron passes from one inner shell to another. However, all the internal forces of complex atoms are completely filled. You know this from the course of chemistry. It turns out that in order for characteristic X-ray radiation to arise, it's necessary that an electron be absent at some internal, close to the nucleus energy level. That is, there must be a vacancy. So, but how can we create a vacant place in a stable atom? Such a vacancy can be formed due to the knocking out of an electron from some internal energy level, but an electron accelerated in an X-ray tube. But how can this be achieved? We said earlier that electrons slow down in the electric field of the anode. But electrons having high energy which bombard the anode, fly to it, are able to overcome the Coulomb's repulsive forces from the outer electron shells of the atoms of the anode substance and interact with the electrons that fill the inner shells of the atom. What's next? And then the electron is released, which is located over the inner shell. This effect is called internal ionization or Auger effect. Auger effect. It's known that the state of an atom with a vacancy on the inner shells is unstable. What does the atom seek to do after this? Yeah, this is the unstable statement for the atom. Fill the vacancy. An electron of one of the outer level fills a vacant place, and the atom then passes to the final state with a lower energy, emitting excess energy in the form of characteristic radiation. But if we are still talking about levels close to the core nuclei, it turns out that a vacancy has formed again and the atom again seeks to fill it with an electron from the next energy level and so on. Therefore, the characteristic radiation always contains a set of spectral lines. All possible transitions of an electron from the overlying layers to the K layers, from the K series you can see, to the L layer, L series, and so on. The spectral lines in each series, which have a minimum wavelength, are denoted by the alpha index, followed by the beta, and so on and so on. And this picks a series. Thus, it turns out that the resulting characteristic radiation is due to electronic transitions in the inner shells of atoms. In this case, the emission spectra of optical range are due to the transitions of valence. In this case, the emission spectra of the optical range are due to the transitions of valence electrons from one state to another. The line spectrum of characteristic radiation is represented as a series. By the values of the wavelength of the lines of the characteristic spectrum, it's possible to determine the belonging of the anticathode or anode material to one or another element of the periodic system of Mendeleev, Mendeleev periodic system. In order to determine this belonging, we will be helped by Moseley's law, which connects the frequency of spectral lines of the characteristic X-ray radiation of an atom with its serial number, which, with an increase in serial number of elements, the frequency of the X-ray photon also increases, according to Moseley's law, where Z is the ordinal numbers of the element and A and B are constants depending on the line type. So, consider with you the interaction of X-ray quanta with atoms and molecules of the substance in which they propagate. Obviously, the result of this primarily depends on the energy of quantum. And you and I realized that X-ray radiation causes ionization of molecules, which means that there will be situations when this energy is not enough and excess. Let's consider all these cases. There are 4 types of interaction in total. Let's start firstly. The classical situation, first part. The classical situation when the energy of quantum is not enough to ionize the atom. What then happens in the atom? Then quantum energy are scattered on the atom or the substance without changing their frequency. Let's look at the picture, And this interaction is called coherent scattering. It's typical for long-wave soft X-rays. Coherent scattering leads to a change in the structure of incident X-ray beam. If the beam incident on the substance was parallel, then quanta appear that propagate in different directions, being partially or completely absorbed by the substance. What is actually happening? The flux of X-ray photons falls on the atom, change its direction, and nothing changes. According to the law of conservation of energy, the energy of the photon of the incident quantum is equal to the energy of the photon of outgoing quantum. So, second part. Consider the following situation. When there is enough energy to ionize an atom, it's even more than enough. In this case, the electron is detached from the atom and acquires some kinetic energy. The photoelectric effect occurs. As a result, the absorbed energy of the X-ray quantum causes the ionization of the substance and the excitation of atoms and molecules. Again, the law of conservation of energy is fulfilled. That is, what falls and what the energy turns into a quantum with an energy. This H nu or HF and is spent on knocking out an electron, kinetic energy, and ionizing atoms. So quanta come to atom, and this energy enough to ionizing, and after that we have an ion and electron which go out from atom. So this energy is enough, and according laws, this energy is to kinetic energy and ionization. So it was photo effect. What is the next? The next type of interaction when the energy is even more than necessary for the ionization of the atom, that is, much more than it's necessary for ionization. What happens in this situation? Parts of energy of the H nu or HF of the incident quantum is spent on turning out an electron from the electron shell to the atom of the substance. This electron is called the recoil electron, and the other part for the formation of the photon of lower energy, H nu with apostrophe, H nu or HF with apostrophe. And another direction of propagation, as well as for imparting kinetic energy to the detached or free electrons. This phenomenon is called the Compton effect. What is about or Compton scattering? This is a phenomenon of scattering of quanta of electromagnetic radiation quanta by free or weakly bound electrons with atoms, and the scattering of X-ray with a change in wavelength in incoherent scattering. The result of such interaction are as follows. According to the law of conservation of energy, the energy of incident quantum is consumed, and the energy of the secondary quantum is naturally less than the energy of primary incident quantum, really. If the kinetic energy of the recoil electron is large enough, then it can ionize neighboring atoms, this electron, and thus creating secondary X-ray radiation. And also, the primary quantum H nu or HF with Compton scattering can't completely transfer all its energy to the electron. Quantum gradually loses its energy, changing direction with each next interaction. The number of acts of scattering of quanta can amount to tens. The path of the wandering quantum is an unpredictable broken line. Sooner or later, the quantum will lose energy so much that for it the most probable interaction will be photoabsorption. And accordingly, the lower probability of Compton scattering when energy is expanded, the greater the probability of photoabsorption or photo effect. Thus, hard X-rays, due to the Compton effect, which occurs independently and in parallel with the photoelectric effect, and secondary processes, cause significant ionization of the substance with which they interact. As a result, when the biological tissue is exposed to X-rays, strong structural and functional changes occur in the later. And the last most complex type of interaction, which is already associated with gamma quanta, is the formation of electron-positron pairs or pairing. The formation of pairs is a reaction in which a photon of sufficiently high energy flying through a substance under the influence of a sufficient strong electric field near the nucleus of an atom turns into an electron-positron pair. X-ray and gamma-ray quanta, which we have the same wavelength or frequency, are absolutely the same in all parameters. Let me remind you that they are distinguished only by their origin. X-ray arises from the interaction of fast electrons with electrons of matter, and gamma radiation is the result of processes occurring in the nuclei of the atom. So, everything that happens in an atom outside the atomic nucleus is manifestation of electromagnetic interaction. Processes of much higher energy level occur in atomic nuclei, which are characteristic of strong and weak nuclear interaction. Even the byproducts of internuclear processes are hard gamma rays with quantum energies often exceeding 1 mega electron volt. If this energy of quanta of electromagnetic radiation is more than 1 mega electron volt, the process of interaction of radiation with matter unthinkable in classical physics. The process of formation of electron-positron pairs can occur. The formation of electron-positron pairs occurs if a quantum with energy h nu is more than 1 mega electron volt is in the field of atomic nucleus. So one might say when a quantum solid collides with a nuclei. The primary gamma quantum with an energy exceeding the threshold value of 1 mega electron volt spends it on the formation of an electron-positron pair, and all excess energy is realized as the kinetic energy of the electron and the positron. The excess energy is divided equally between them. The higher of energy of gamma quanta is greater, the greater the probability of the process of formation of pairs become. The probability of an alternative process, Compton scattering, is gradually decreasing. When the energy of primary gamma quanta is more than 2 mega electron volt, the process pair formation is predominant. And it's also important that Compton scattering and the photoelectric effect can be accompanied by characteristic X-ray radiation, since after knocking out the inner electron, the vacant places are filled with the electrons of the outer shells. The considered interaction of radiation quanta with matter lead to the facts that when passing through a layer of matter, the radiation intensity decreases. Its weakening occurs due to two processes. Absorption, when the energy of X-ray quanta is spent on structural rearrangement in matter, quanta cease to exist, and scattering, when X-ray quanta change their primary direction of propagation. So, if a parallel X-ray beam or rays with intensity I0 falls on a layer of matter, then when passing through a layer of matter with a thickness of X, intensity of radiation propagating in the same direction takes on the value I intensity. Attenuation of radiation occurs according to the same exponential law as for light rays. In the formula, you can see this is a Booger law. You can see in this formula I0 is the intensity of the incident radiation. What is about I? Is the radiation intensity after attenuation by the medium. E is exponent, and exponent is represented in the power minus mu x, where x is the depth of penetration of radiation into the substance, and coefficient mu is the linear attenuation coefficient that characterizes the decrease X-ray intensity due to absorption and scattering per unit layer thickness. Then, linear attenuation coefficient depends on the nature of the material that absorbs the radiation and one of the wavelength of the absorbed radiation. Graphically, the law of attenuation is an exponential law. That is, the radiation as it passes deep into the substance will decrease exponentially. For practical calculations, the mass attenuation factor is used in practice as an attenuation characteristic. It's the ratio of linear index to the density of the substance. When considering the law of attenuation of the Bremsstrahlung X-ray radiation flux in matter, it should be taken into account that this radiation contains quanta of different energies. Therefore, they have different penetrating power. The coefficient mu in the formula is constant for a given substance only for monoenergetic X-ray radiation, a certain wavelength. For a qualitative assessment of the penetrating power X-ray radiation, the concept of half attenuation layer is used in practice. What is about half attenuation layer? You can see its parts on this part. What happened? This is a thickness of the absorber layer, which attenuates the intensity of the incident radiation by a factor of 2. In the figure, the half attenuation layer is shown in the graph of the dependence of the intensity X-ray radiation I on the thickness of the layer X, the substance through which it passes. The relationship between half attenuation layer and attenuation mu, coefficient mu, can be easily established analytically. Let's look at Booger's formula and replace our layer thickness X with the value of the half attenuation layer, d half, and therefore the radiation intensity will also decrease by a factor of 2. Then we have the following. If we can say that intensity, full intensity, after attenuation, we can put it the divide, because half attenuation layer, half intensity. Put this half in spite of intensity, and what happened? We have that the dependence between half attenuation and coefficient mu is like in this formula. When the radiation passes through the half attenuation layer, its spectral composition will change. The radiation will become harder, since shorter X-rays have greater penetrating power and soft radiation is absorbed more strongly. Therefore, the second half attenuation layer will be thicker than the first. So, now let's see the properties of X-ray radiation with description and how can we apply this property in medicine. There are many properties. We will say about only 7 properties according to this table. Let's start from the first. First property is penetrating ability. What is this? The ability to penetrate substances and media that are opaque to visible light. And we can use this penetrating ability in X-ray image acquisition, So, next is different absorption of radiation by media. The ability to be absorbed by media depends on wavelength and properties of the substance, and we can put it in obtaining an X-ray image. We know that X-rays have a rectilinear propagation, so they propagate by a rectilinearly diverging beam, and the skyology will be special. Skyology, this is a science of shadows, which we use in X-rays and in medicine too. Next is fluorescence. What is it? This is ability to induce a glow of phosphorus. We use it in traditional fluoroscopy. Photochemical action. The ability to light up photographic materials, the composition of silver bromide. And we can use it in radiography and X-ray tomography. Next is decrease of radiation intensity depending on distance. And this is the special property which we can use in medicine, really, because the radiation intensity is inversely proportional to the square of the distance between X-ray tube and the irradiated objects. And its main protection, our protection from X-ray. This is distance, and we can use this in X-ray therapy too, according to this decreasing. So next is ionizing action. The ability to convert an electrically neutral medium into an electrically conductive medium. The ability to form ions, in ionizing action, special part, and we can use it in X-ray therapy and dosimetry. And last is biological effect, especially without biological effect, ionizing radiation can't be. So the ability to induce changes in biological tissue, but we can use this application in X-ray therapy to defeat the oncology, for example, or cancer. So, due to the different structure of tissues and organs that make up our body, their absorption of X-ray is different. Therefore, when exposed to X-ray radiation, a shadow image of the internal organs appears, which is observed on a luminescent screen or fixed on photographic film. For X-ray diagnostic, radiation with photon energy is used, in which the primary processes of its interaction with matter are determined mainly by the photoelectric effect. It's known that the morphological structure that forms the human body differ more in chemical composition. The more clearly the image on a screen or photographic film, the difference in absorption rates is great. For example, the image of bones is very clearly manifested against the background of the image muscle tissue or other soft tissue. X-ray, a method of X-ray examination in which the image is fixed on the solid carrier and X-ray film. X-rays are generated in an X-ray tube, pass through the patient's body and onto X-ray film. X-ray film contains silver bromide, which, when exposed to radiation, decomposes with the formation of microparticles of metallic silver. After photochemical processing of the film, an image appears in the form of various shades of gray, and the image of the film is negative. And there are advantages and disadvantages of this method, really, of this diagnostic method. And let's see what advantages can be. High resolution, objectively, of the method. Low radiation exposure for the patient and the doctor, because it has short and exposed times, and the time to study the X-ray is not limited. But it has disadvantages too. Limited ability to study organ function. We can't we can't see the organ function using simple X-ray radiography. Impossible polypositional exploration and X-ray palpation. What is next? Fluoroscopy. This is a method of X-ray examination when the image is obtained on a fluorescent screen or video monitor in real time. The principle of the method. What is? X-ray radiation is generated in an X-ray tube, passes through the patient's body and hits a fluorescent screen or an image intensifier. X-ray intensifier, which transmits the image to the display, and the image on the screen is positive. Yeah, but this method has advantages and disadvantages too. Let's see. The ability to study the function of organs, possibility of polypositional research, and X-ray palpation possible. But it has disadvantages too. What is? High radiation load because it has a long exposure times. Subjectively of the method and research time limit. Next method is fluorography. I think you know about this method. What is this? The image obtained on the screen is photographed of a sensitive small format film. This diagnostic method, fluorography, is X-ray examination based on photographing an image obtained on a fluorescent screen. And what happened? Fluorography is widely used in mass screening of the population. If pathological changes are found on the fluorogram, then the patient is prescribed a more detailed examination. X-ray radiation is generated in an X-ray tube, passes through the patient's body, and hits an X-ray screen covered with a special compound, phosphor, which glows under the action of radiation, and the image appears on the screen. This image is automatically photographed by a special camera on a photographic film. The photographic film is processed in solutions and examined with the magnifying optics. And on the slide you can see advantages and disadvantages too. You can read it yourself. Next is digital radiography. In digital radiography, an X-ray projection image is not formed on an X-ray film, but using a special digital X-ray image receiver. The practical application of digital X-ray diagnostic method radically leads to a change in the entire technologies of patient researches. You can see the advantages of method are follows advantages. Yes, there are many advantages of this method, but it's still there. Therefore, the method is also ionizing, and which means that there must be appropriate indications for its appointment, especially in children. But not forget about high cost of equipment. So you can read from the slide advantages and disadvantages yourself, please. All of the above diagnostic methods are, of course, relevant today. But science does not stand still. In medicine, a diagnostic method was needed that would allow obtaining an image not on a plane, but still in volume, when we could assess the anatomy and topography of an organ, its size, level of damage in various diseases. And such a diagnostic method was created in the second half of the second century by scientists Hounsfield and Cormack. This is a computed tomography method. To obtain a high-quality image, it's necessary to use as many projections as possible. Computer tomography or computer tomography scan, or we can say CT, allows you to process a huge number of projections. CT scanners create a digital image by measuring the intensity of X-rays that pass through the body as the X-ray tube rotates around the patient. The method is also based on an X-ray tube too. The main difference is that in a computer tomography, it's movable, rotates. The examination table on which the patient lies in is also movable, and detectors, sets of detectors, rows of detectors acts as radiation receivers. If we are talking about multispiral computed tomography, X-ray detectors record the intensity of radiation that has passed through the patient tissue, provided that such a system contains one detector and one source of X-ray radiation. Then, in one turn of the system process 360 projections. The number of such detectors reaches hundreds. Transmission is carried out in thousands of directions. And on the slide, you can see advantages and disadvantages too, like as in other methods. Yeah, you can read it yourself. Now, let's move on to talking about radioactivity. The history of the physics of the atomic nucleus is usually counted from 1896. This year, Henri Becquerel made an important discovery. While studying the phenomenon of phosphorescence, he discovered that one of the minerals containing uranium has the ability to light up photographic plates, even if they are wrapped in opaque paper. It was clear that the mineral emits some kinds of new radiation and emits spontaneously in constant, for example, to X-rays. The new phenomenon is called radioactivity. After 2 years, Pierre Curie and Maria Skłodowska-Curie discovered the radioactivity of thorium and isolated two new radioactive elements, polonium and radium. A detailed experimental study of radioactive radiation was carried out by Rutherford. He investigated the physical properties of a new type of rays and showed the radioactive radiation consists of 3 types of rays. Hereinafter called alpha, beta, and gamma rays. The fact that the phenomenon of radioactivity is associated with a process taking place in the atomic nucleus was clear, but the internal structure of the atomic nucleus remained unknown for physicists for many years. Later, researchers managed to understand that the nuclei of a number of atoms, radionuclides, are subject to spontaneous transformations, which result in ionizing radiation in the form of quanta of electromagnetic energy and elementary particles. This radiation interaction with biological tissues have a strong effect on biological objects and lead to strong structural and functional changes. As we discussed earlier, radioactivity is a spontaneous decay of unstable nuclei with the emission of other nuclei or elementary particles. Radioactivity is natural and artificial. Natural radioactivity occurs in unstable nuclei that exist in natural conditions. Artificial radioactivity is the radioactivity of nuclei formed as a result of various nuclear reactions. You should know that the structure of the atom better than I do from your chemistry course, I think. Atomic nuclei are composed of photons and neutrons, which have a generalized name nucleons. Nucleons, yeah. The number of photons is in the nucleus determines the chemical properties of the atom and denoted by Z. This is the ordinal number of chemical element. The number of nucleus in a nucleus is called the mass number and is designated A, letter A. So, nuclei with the same serial number and different mass numbers are called isotopes. All isotopes of one chemical element have the same chemical properties. The physical properties of isotopes can vary greatly. The decay ability of a nucleus depends on its composition. The same elements can have both stable and radioactive isotopes. For example, the carbon isotopes is stable, while 14th isotope is radioactive, for example. So, a microscopic sample of any radioactive isotope contains a huge number of radioactive nuclei. These nuclei don't disintegrate at the same time. The decay process is random and does not depend on external conditions. For a single nucleus of radioactive atom, it's impossible to predict the time during which it will decay. One can only draw conclusions about the probability of a given event. But using the theory of probability, you can really predict how many nuclei of the sample decay in a given period of time. For a large set of nuclei, it's easy to obtain statistical law that expresses the dependence of the number of non-decayed nuclei on time. It's established on the basis of the following considerations. We will assume that the number of nuclei dn decays in a short time interval dt. Obviously, this number is proportional to the time interval dt and the total number of non-decayed radioactive nuclei n by the moment. Then we have a differential equation that describes the decay process. This equation, the minus sign indicates the decrease in the number of non-decayed nuclei with time, and the coefficient lambda depends on the type of nuclei and is called the decay constant of nuclei per unit time. Now we introduce the initial condition for this equation, that the number of atoms at the initial moment of time is n0. N is n0, time is 0. So the solution of the differential equation, taking into account the introduction of initial condition, will present the formula to us in the following form. You can see. This expression starts stating that the number of radioactive nuclei of a given isotopes decreases with time according to an exponential law. It's called the law of radioactive decay. The rate of radioactive decay is determined by the atom, including the exponent of the decay constant lambda. You can see constant lambda, that is decay constant. In practice, instead of the decay constant, a value uniquely associated with its used a half-life, the time during which half of the radioactive nuclei decay. Half-life, the period of time. So the half-life can be determined by or from the graph in the figure. Let us now establish with you the analytical connection between the decay constant lambda and half-life. For this, we substitute the equation that time is big T period, yeah? This period half time T. Then we have the formula. Let's transform the resulting expression and get. And it turns out that the law of radioactive decay when using the characteristic big T is as follows, yeah, half-life. Note that the decay constant lambda is measured in units, yeah, in units, reciprocal of time, and the half-life T is determined in second, hours, years, and it's etc. Yeah, half-life is the main quantity that characterizes the rate of radioactive decay. The shorter the half-life is, more intensive the decay proceeds. You can see. To characterize the rate of radioactive decay of nuclei, the concept of the activity of the radioactive preparation equal to the number of decays per unit time is introduced. The activity of radioactive preparation is its most important characteristic and determines the effect on biological object of gamma protons and particles arising from the decay of radionuclides. The activity of a radioactive drug is the number of unstable atom of that drug that decay in 1 second. In the system international, the unit of activity becquerel is adopted in honor of Antony Becquerel, one of the first researchers of radioactivity. 1 becquerel is 1 decays by second, and one by second. The off-system unit of activity, Curie, is also widely used. 1 Curie is 3.7 multiplied on 10 to the power 10 becquerel, or the same number, or 1 divided by second. The value of 1 Curie, is a very, very large value. In medical practice, drugs with activity in milli and microcurie are used. 1 millicurie is 10 to the power minus 3 curie, and etc. Activity, by definition, is an indicator of the decay rate, the number of decays per unit time. While the law of radioactive decay N is the number of nuclei that have not yet decayed. Taking the derivative n, first derivative n is dn by dt, of the function in our radioactive decay, we get the equation describing the activity of the drug as a function of time. The function of time, really. The minus sign in this expression indicates the radioactive decay function is decreasing, and the rate, dn by dt, of this decay decreases exponentially, like the number n in decay equation. So, let us now consider with you the types of radioactive decay. Let's start with alpha decay. Alpha decay is a decay of an unstable nucleus into a daughter nucleus and an alpha particle. This type of decay is characteristic of heavy atomic nuclei with a mass number more than 140. An alpha particle is a fragment of the parent nucleus consisting of 2 protons and 2 neutrons combined into a helium nuclei. Alpha decay occurs according to the following scheme. You can see, this scheme on the slide. But why does the nuclei emit an alpha particle and not individual nucleons? This happens because the mass of an alpha particle is significantly less than the sum of the masses of the 4 nucleons that make up it. Therefore, such decay with the formation of 2 protons and 2 neutrons is, in principle, impossible since the sum of the masses of the products of this post-reaction is greater than the mass of the parent nucleus. It should also be borne in mind that new nuclei formed during decay can be subject to further radioactive transformation until a stable nucleus is formed. Next time of decay is beta decay. Beta decay is a spontaneous process in which an unstable initial nucleus turns into an isobar nucleus. This decay is explained by the transformation in an radioactive nucleus of a neutron into a channel of or a proton into a neutron. It was found that beta decay is always accompanied by the emission of neutral particle, a neutrino or antineutrino. This particle practically does not interact with matter. The energy released during beta decay is randomly distributed between the beta particle and the neutrino. Therefore, the energy spectrum of beta radiation is continuous. Beta decay can generate gamma radiation. Obviously, for beta decay to be possible, it's necessary that the mass of the parent atom be greater than the sum of the masses of the daughter atom and the beta particles. The difference in the masses of these atoms should determine the kinetic energy of beta particles formed during decay. Thus, beta particle must have a kinetic energy value that is quite defined for each beta radioactive element. Experiments have shown that only individual particles have energy close, and the energy of most beta particles is significantly less than this number. In addition, careful measurements of the momentum and the angular moment of the mother and daughter nuclei and of the beta particle have shown that these quantities are also not conserved during beta decay. So, it would seem that the fundamental laws of physics are violated. The laws of conservation of energy, momentum, and angular momentum. Subsequently, it was provided that during beta decay, along with the electron, a neutral particle escapes, which carries with it a part of the energy, momentum, and angular momentum. This particle is neutrino, like as a small neutral, we can say. Later, a particle appearing in beta decay together with an electron began to be called an electron antineutrino, and a particle appearing in beta plus decay together with a positron and electron neutrino. In accordance with this, there are three types of beta decay. Let's start with electronic beta minus decay. In this case, the nucleus of radionuclide emitting an electron forms the nuclei of a new element with a serial number one more than original one. The question may arise, where does the electron come from if? According to the nuclear model, there are no electrons in the nucleus. There is no contradiction here. Since the formation of electron occurs due to intranuclear transformation of neutron into a proton. A detailed examination of this decay with the calculation of the energy of neutron and the decay products shows that along with the proton and the electron, another electrically neutral particle with a negligible mass was called a neutrino should be arise during the decay of a neutron. More precisely, an antineutrino appears during beta minus decay. Naturally, due to their low mass, lack of change, and accordingly colossal penetrating power, the neutrons and neutrinos and antineutrinos are very difficult to detect experimentally, although experimental confirmation of their existence has been made. The difference between neutrinos and antineutrinos is that the first particle has spin directed along the motion and the second again. So you can see the scheme of this decay and the scheme of how can we formate electron due to transformation of neutron into a proton, and the scheme of this decay. So next decay is positron or beta plus decay, we can say. In this case, during decay, a positron is emitted and nucleus of a new element is formed, the ordinal number of which is one less than the initial one, and another neutrino appears. A positron is formed as a result of the intranuclear transformation of a proton into neutron. You can see the schemes too on this slide. So, and the last one is electronic capture or E-capture. Is that the electron belonging to one of their inner shells of the atom is captured by the nucleus, as a result of which the proton of the nucleus turns into a neutron with a release of neutrons. Since this type of radioactivity frees up space for an electron in the inner shell on the atom, the electron moves to this place from the shell farther from the nucleus, and which gives rise to characteristic X-ray radiation during electron capture. You can see the scheme in the slide too. And gamma radiation is electromagnetic radiation. It can also be thought of as a stream of photons, quanta, with very high energy. The emission of gamma radiation by a nucleus is in many ways similar to the emission of photons by excited atoms. Like an atom, the nucleus can be in an excited state. Upon transition to a lower energy state or ground state, the nucleus emits a proton. The allowed energy levels of the nucleus are separated in energy significantly more than the energy levels of the atom. The distance between neighboring levels in the nucleus of the order to magnitude and numbers of energy, numbers of voltage, energy electron volt from 10 to the power 3 by 10 to the power 6 compared to 10 electron volt in the atom. Consequently, the energies of the emitted gamma quanta can vary from units of kilo electron volt to mega electron volt. The gamma radiation spectrum is always discrete, since the energy levels of the nucleus itself are discrete. Gamma radiation, unlike alpha and beta radiation, does not carry a charge, and it's not associated with a change in the internal structure of nucleus. Therefore, the process of emission of gamma quanta is not accompanied by a change in the charge of or mass number, and at the same time there is no transformation of one chemical element into another. The transition of a nucleus from the excited state to the ground state is accompanied by the emission of one of several gamma quanta, the energy of which can reach several mega electron volt. So, most often alpha and beta decays are accompanied by gamma radiation. Don't forget about it. Let us now consider with you the features of interaction with matter of various particles. Alpha particles. Firstly, alpha particles are highly ionizing, as the alpha particle moves into a substance, the ionizing density first increases, and then partially at the end of the run it drops sharply. The average linear range of an alpha particle depends on its energy and properties of the substance. In air, it's equal to several centimeters, yeah? In liquids and biological tissues, microns. Despite the small depth of penetration of alpha particle into biological tissue, their destructive effect is very significant due to their high ionizing ability. In addition to ionization, a number of other effects develop during the interaction of alpha particles with a substance. Excitation of atoms, the appearance of characteristic X-ray radiation, radioluminescence, and etc. A more rare process in the interaction of alpha particles with the nuclei of atoms that make up the substance. In this case, nuclear reactions are possible. Beta particles, having a lower charge and significantly less mass in comparison with alpha particles, also have a lower ionizing ability. Due to scattering on electron or of substance, when it propagates in it, beta particles strongly change their primary directions of propagation. The depth of penetration of beta radiation into body tissues is 10 to the power minus 15 millimeters. In addition to ionization, due to the deceleration of electrons in the substance, Bremsstrahlung X-ray radiation arises. When positrons hit a substance, they can annihilate with electrons, forming gamma quanta. Gamma radiation. Being very short electromagnetic waves, this radiation is more rigid than X-rays. Also, the primary mechanism of interaction with matter are in many respects similar. In the primary acts of interaction, coherent scattering is of lesser importance here, since it manifests itself for quantum energies lower than the ionization energy of the atom. A gamma photon has a higher energy than an X-ray quantum, and due to the photoelectric effect and incoherent scattering, when it interacts with matter, scattered secondary high-energy gamma quanta and electrons that ionize the medium are formed. In addition, high-energy gamma quanta in the force field of nuclei of atoms of a substance can cause the formation of electron-positron pairs. Since during the propagation in matter, gamma radiation causes a number of secondary processes, the exponential law of attenuation of its intensity is fulfilled approximately, especially for high-energy gamma quanta. The penetrating power of gamma radiation is very high. In air, and the average path length of quanta exceeds tens and even hundreds of meters. The human body is almost completely penetrated by them. And last is neutrons. And despite the lack of charge on the neutron fluxes also ionize matter. The ionizing effect occurs due to complex processes. This can be fission of nuclei during the capture of neutrons, due to which radioactive fragments, charged particles, and gamma radiation are generated. Nuclear reactions can occur with the release of photons and alpha particles. Since, due to the lack of charge, neutrons penetrate deeply into the substance, protection from neutron irradiation is a difficult task. Fast neutrons must first be slowed down, for which hydrogen-containing substances, for example, water, are used. Then substances are used as the actively absorbed neutrons, for example, cadmium absorbers. And we must say some words about radionuclide diagnostic methods. Radionuclide diagnostics is based on the use of radionuclides or chemical compounds labeled by them. All radionuclide techniques are associated with the introduction of radiopharmaceutical into a patient's body or into tissues and fluids extracted from the body. Radionuclides introduced into the body are sources of gamma radiation, which is recorded by special detectors. Then the data is processed. So, what are the requirements of radiopharmaceuticals? Firstly, when decaying a radionuclide should emit particles that are easily detected by appropriate equipment. Alpha decay or alpha active radionuclides are not suitable for diagnostic purposes. Even in a very thin layer of biological tissue, they are quickly absorbed and can't be registered. Beta particles can be detected only when they are emitted from thin surface layer of the body. Therefore, gamma-emitting radionuclides are of the greatest importance in diagnostics since gamma quanta are easily detected due to their high penetration ability, even if they come from deeply located internal organs. Secondly, moving with the flow of body fluids or being involved in metabolism, radiopharmaceuticals emitting gamma quanta should reflect the function of the organ or body of interest to the diagnostician. The third, the injected drug should create a minimum radiation load on the body. This is achieved by using radionuclides with a short half-life and drugs that are quickly excreted from the body. The period of half the disappearance of radionuclides from the body due to the processes of physical decay and biological extraction should approach the time of diagnostic examination. And we must say some words about methods in radionuclide diagnostics. Let's discuss them. Radiography or gamma chronography is a first method, is a method of functional research, which is based on the study of the dependence of the intensity of gamma radiation from an organ after the administration of radiopharmaceutical on time. Though such studies, it's possible to judge the movement of blood through the vessels and chambers of the heart, the functioning of the liver, kidneys, lungs, and other. And the slide shows an example of radiographic examination of kidneys. As a result of radiography, we obtained radiographic distribution curves of the radiopharmaceutical in the examined organ. The intravenous radioactive drug is carried in the blood into arteries of the kidneys. This causes the rapid appearance of radiation above the kidneys, increasing part of the curve. Then the contents of the tubules drain, and within a few minutes an approximate equilibrium is created between the intake and decreases of the radioactive preparation, which corresponds to the top of the curve. And subsequently, the outflow begins to prevail over the incoming, and the number of gamma quanta entering the detector per unit of time decreases. This causes a decrease in the curve. Analysis of the data obtained by this method provides detailed information about the functioning of the kidney. It's possible, for example, to detect predominant violation of the flow of the drug into the kidney, along the ascending branch of the curve, or violation of excretion. So, with urolithiasis, the overlap of the ureter with the stone leads to the fact that the descending branch of the gamma chronogram runs almost parallel to the abscissa axis. The next diagnostic method is scintigraphy. Scintigraphy is a method of radionuclide diagnostics based on visualization of the distribution in the body of radionuclide introduced as part of radiopharmaceutical. How does the diagnostic process take place? The radiopharmaceutical is injected into the body. A gamma camera detector records activity just over a large scanned area. Gamma quanta interact with a scintillation crystal in a gamma camera detector, creating microscopic flashes of visible light, scintillations, and are detected and amplified by a photomillimeter tubes. Electrical signals undergo computer processing and form an image on the screen. A scintigram is a functional anatomical image. This is the uniqueness of the method which distinguishes it from ultrasound, CT, MRI. Therefore, a prerequisite for the appointment of scintigraphy is the presence of functional activity of the organ. Otherwise, the image will not work. Scintigrams are able to reflect physiological and pathophysiological changes in the body. This is achieved through the use of radiopharmaceutical capable of accumulating in certain morphological structures or reflecting the dynamics of physiological or biochemical processes occurring in an organ. The slide shows an example of scintigram of liver and spleen, you can see. And the next method is positron emission tomography. And the special method with combined with positron emission tomography, it may be PET-CT and PET-MRI. So let's start. It's a medical imaging technique based on the use of positron beta plus decaying radiopharmaceuticals. Research is carried out on a special gamma camera with movable detectors. Tomographic radionuclide studies allow obtaining images from a separately selected tissue layer. In this study, radiopharmaceuticals are used that from positrons during their decay. The resulting positrons interact with electrons in the tissues of the body. In this interaction, annihilation, paired gamma quanta are formed, which are recorded by detectors. Ultra-short-lived radionuclides are used for research. The slide shows the example of diagnostic, the same type of pathology in computer tomography. This pathology part. Only positron emission tomography and combined positron emission tomography and computer tomography. So, further, it will be logical to move on to discussing therapy with the help of various types of radiation. Radiation therapy is the method of cancer treatment based on suppressing the activity of pathogenic cells using ionizing radiation. Radiation therapy uses various types of radiation. When using radiation therapy, it's necessary to most intensively influence the focus of pathology with radiation with minimal energy absorption in the surrounding healthy tissues and organs. This is a very serious problem, and some of the methods for resolving it for each specific case of treatment consist in the optimal choice of radiation with certain physical properties and method of exposure. Let's consider some of the features of radiation used for radiation therapy. Firstly is alpha therapy. It's based on the use of short-lived alpha-emitting isotopes, taking into account the fact that their range in body tissues is no more than 0.1 millimeters. These particles have a significant linear ionization density and are absorbed by even a small layer of air. Therefore, the therapeutic use of alpha rays is possible by directed contact with the surface of an organ or by introducing it inside using a needle. For superficial exposure, radon therapy is used. Exposure to the skin, digestive organs, drinking maybe, and respiratory organs, inhalation. Next is beta therapy. Is one of the methods of radiation therapy which consists in irradiating a pathological focus with beta particles of radioactive isotopes. The therapeutic effect of beta therapy is based on the development of biological reaction in pathological tissues irradiated with beta particles, which is based on the death or loss of ability of individual cells to divide. Numerous beta-decaying radioactive isotopes are used as a radiation source for beta therapy. The choice of isotopes depends on both their physical and chemical parameters and the method of application. The birth of beta therapy is associated with discovery of artificial radioactivity, as a result of which it became possible to obtain various beta-emitting radioactive isotopes. Depending on the method of application of the source of beta radiation to the pathological focus, their application intracavitary and internal beta therapy, which must be carried out in compliance with radiation safety. Next method is gamma therapy. It is a type of radiation therapy based on the use of gamma radiation. Sources of gamma radiation are natural isotopes, radium and mesothorium, and artificial cobalt, iridium, tantalum, and other. And special information about the gamma knife. Based on the gamma therapy gamma radiation. Designed for stereotactic radiosurgery, the target can be irradiated with an accuracy of 0.3 millimeters. These are achieved due to the static arrangement of the sources and relatively small distance to the isocenter located at a distance of 400 millimeters from each of the sources. The advantage of the gamma knife installation is many beams from cobalt radioactive sources with activity of each source of 30 curie are directed to one point. The set of sources provides a dose rate in the isocenter about 300 centigrade by minute. The dose accumulated in the target is many times higher than the dose on the surface of the human body. The dose delivered to the tumor leads to its death. In this case, healthy tissues receive a small dose of radiation. Each beam of ionizing radiation is formed by a stationary collimator located on the helmet. The gamma knife system consists of sources of ionizing radiation, the helmet with collimating holes of various diameters 4, 8, 14 or 18 millimeters, and a conch with an electronic control system. Inside the helmet, the patient's head is immobilized and high-energy protons emerging from radioactive source and passing through the helmet's channel converge isocentrically on the target space, and we can help our patients with the cancer of our brain, which we can't use when we can't use the simple surgery. I can say you thank you for the attention and goodbye.